captured a lot of my attention. And of course, this year's Nobel Prize has sparked a worldwide flurry in not only the foundations of quantum mechanics, but the foundations of how we understand and know the universe, as well as applications and technologies that are set to change the world that we live in. I often think that we are at the cusp of the second quantum revolution. The first quantum revolution took place about 100 years ago with Max Planck, Einstein, Niels Bohr, Schrödinger, etc. And they developed what was called the old quantum theory. And then Heisenberg came, they made further advances. Dirac came, they intermixed quantum mechanics with electromagnetism and electrodynamics, and we came up with a new theory, which is called the new quantum theory. But in 1940s, when information theory was being established as a theoretical science through the work of Shannon, only then it came to the realization that information is something that we should be talking about as well. And the beauty of quantum mechanics and quantum physics is that it puts information at the level of physicality. Now, information is something physical. It can be measured. It can be quantified. And there are and another thing that I like about this area is that the mathematics is very simple. And in fact, the physicality defies the mathematics. And I'll be able to explain this aspect in this talk. So I'm going to talk about the 2022 Nobel Prize in Physics, and let me introduce these three proud recipients of the Nobel Prize. We have John Clauser, Alan Aspect, John Clauser, and Anton Zeilinger. And if the Nobel Prize was to be awarded posthumously, then the fourth person in this list would have been John Bell, who actually came up with a theoretical understanding of entanglement and quantum information. But unfortunately, he passed away in 1990. So it is these three fine experimental physicists who actually developed the idea of quantum information, quantum entanglement, and gave birth to the technologies that are now permeating our surroundings. All right, so a bit of global context. As we enter the second quantum revolution, we are seeing a plethora of quantum technologies coming out to the fore. Nations, groups of nations, committees of nations are gathering together and coming up with these ultra-large investments in quantum technologies. These quantum technologies are going to shape how we compute, how we process information, how we store and retrieve information, how we quantify information, and how we are able to transmit information from one point to another in a robust, reliable, eavesdropping-free manner, which is absolutely secure against all classical or conventional attacks. It's going to revolutionize drug discovery. It's going to revolutionize how we transport or locomote from one point to another. It's going to cataclysmically change how we design drugs, molecules, how we plan or optimize manufacturing strategies, and how we distribute information across a very big network. China, of course, along with the United States and Europe, are world leaders currently, and these technologies have now gone into space. So there is quantum communication that happens between terrestrial and satellite entities. Quantum mechanics has redefined how we measure standards, for example. We used to read about solid objects kept in somewhere close to Paris, which were serving as standards for the kilogram, for ampere, for candela. for Tesla. But quantum mechanics is now coming up with new rules, it's coming up with new protocols for defining these standards, and therefore commerce and trade might also change in the wake of these quantum developments. We're trying to measure with greater precision using quantum mechanics. There's a worldwide race in making quantum computers bigger and bigger, scaling them up so that we can break the quantum ascendancy limit, as it is called, so that we can do useful computations which are hitherto impossible using classical computers. And of course, there's a lot of deep physics inside it. It's getting into financial magazines, economics magazines. So I think it's really changing the world that we live in. And no scientist, especially a scientist coming out from the School of Science and Engineering, can remain aloof to what quantum mechanics harbors. All right, so I'm really happy that our undergraduates do take a first course in modern physics. The modern physics course is just the tip of an iceberg, and I'm sure that many students from the SSE would foray into this area as they graduate. Now this is a picture, now these pictures have become very popular on the internet. This is a picture of what is called the scaffolding of a quantum computer, one kind of quantum computer. It's really a dilution refrigerator that cools down your quantum computer. So this is a cutaway section of a dilution refrigerator. It's like a big thermos. You remove the outer jacket and that's what you find inside. This is a cobweb of wires, gold-coated wires that are carrying microwave signals, and the sample is somewhere here, and all of this is kept at sub-Kelvin temperatures. Very cold, very cold. So this is one kind of a quantum computer. All right? But you can imagine that it totally looks different from these computers. And there are many different kinds of quantum computers. There are different implementations, different platforms. But this is just one of them, and the most popular of them. Superconducting quantum computers. Now, a little bit of background first about quantum mechanics. And what's so special about quantum mechanics? What's the quantum in quantum technologies? Why does it defy common sense? Why is it counterintuitive? Why does it baffle us? Why does it surprise us? And what's the big deal about it? So I just want to give you a brief overview of the salient features of quantum mechanics, a little bit of history. At the turn of the 20th century, it was generally thought that we'd done all of physics whatsoever. There was nothing new to be discovered. It was like a standstill situation. People were just finding certain fundamental constants to greater degree of precision or accuracy. But then all of a sudden Max Planck came, and Max Planck just looked at the light emanating from a hot object and found out the spectrum of this object. And it appeared that if you were to use the laws of classical physics, Newtonian physics, normal thermodynamics, you wouldn't be able to explain a spectrum that you see of a particular object at a particular temperature. If the temperature goes up, this spectrum shifts to the left to shorter wavelengths. And now smithy or blacksmith workshops have existed for millennia. And one knows that the color of an object that is placed inside a furnace changes as the temperature changes. But there has never been a proper explanation until quantum mechanics and Max Planck's ideas of quantization appeared. So this gave birth to the idea of quantum mechanics, and as the word tells it, it's the quantization of energy that is at the heart of quantum mechanics. And then the second kind of experiments that were performed very early on were in the first decade of the 20th century. The idea was propagated and proposed by Einstein. He was a theorist, of course, and Millikan in 1911 then came up with this experiment which is called the Millikan's photoelectric experiment, which described the quantization of light and the quantization of matter. So these two experiments, looking at the colors from a hot object and how the photoelectric effect works are at the heart of quantum mechanics, and they actually catalyzed and seeded the initiation of this discipline that separates quantum mechanics from the rest is, as the word tells you, quantum. Quantum really means quantization, discretization. And here in this picture, there are many different experiments that one can design that can show the quantumness of matter, quantumness of atoms. In fact, in the 18th century, when astronomy was developing and when some of the finest instrument makers were making telescopes and spectrometers, and one pointed the spectrometers towards the different stars on the night sky, one could find characteristic spectra, which are very much like a spectrum that I'm going to show you in a minute. But the idea is that atoms or molecules have discrete atomic energy levels, and whenever an electron makes a transition between these discrete steps, a finite amount of energy is emitted. So let me give you an example here. So if I'm standing on this chair, so if I stand on this chair, I'm at a particular energy level. The height of the chair is fixed, and I cannot hover in between the ground and this pedestal. I can only stand on this pedestal, on the cushion, or on the ground. I cannot lie anywhere in between. So my position is discretized. And if I were to make a jump back to the ground, my energy is going to drop, right? And that finite amount of energy drop results in the emission of radiation or light. And this light, since it's precise in energy, its frequency or wavelength or color is also precise. So if I were to make a periscope of this kind and put a small opening or orifice at its end and point it towards the sky and connect a spectrometer with it, I would obtain a spectrum of this kind. So this is a spectrum that we've taken on the SSE lawns. Now there are discrete blips in this spectrum. This corresponds to the atmospheric gases absorbing precise wavelengths. So the converse is also true. If excitation occurs, if an atom is demoted from a high level to a lower level, energy is emitted. And if precise energy is shown onto a molecule or an atom, energy is absorbed. This is what is happening over here. To give you a simple example of this phenomenon, what I have in front of you is something very simple. This blue thing here is a spectrometer, is a box, okay? And it's going to take up light from any source, and we're going to see what the spectrum looks like. So this is the most vivid and clear example of quantization. So I'm going to open up the software for this, which shows the spectrum. So all right. So I just turn on my, can I have a mobile phone? I just need a light. Can you turn on the light? So on the screen you're seeing a spectrum. This axis is the wavelength, and you will have the intensity on the y-axis. And I'm just shining some normal LED light onto this. So the intensity is very large. All right. So this is a non-quantum spectrum, right? So this light that is coming from the LED has this range of wavelengths, and it's continuous, nothing quantum about it. All right, it's a hot object. LED is this sequence. This is an LED source which is emitting white light. Now let's look at something more interesting, something that can reveal the quantum mechanical nature. What I have is the tube. Here's the tube, and it has one of the most abundant elements in this universe, which is hydrogen. So this is a tube that has hydrogen in it. and it has electrodes on the top and bottom side, and I just want to put this inside this tube holder. Okay, I'm going to turn on this tube. Let me turn off the lights for a minute. Just need to remember which ones. Alright. Let's see what kind of spectrum do we get. Do we see this quantization? Now hydrogen is a simple element. The simplest element you can think of. Just a proton and an electron. And in this tube these atoms will get ionized. But nevertheless it's just a proton-electron system. So let's see. Alright. So first of all you can observe a nice pink coloration. The high voltage actually disturbed the batteries a little bit. So this has about 5 to 10,000 volts in it. But here now you see a line spectrum. Precise wavelengths being emitted by this hydrogen. And the reason is that we've excited the hydrogen and the electrons have been promoted to a higher level, and there's a large number of higher levels available. And when those electrons come down to one particular shell called the L shell, visible light is emitted. Since this spectrometer is a visible spectrometer, we're focusing on the visible part of the spectrum. And these are precise lines. And this is a precise wavelength, say 760 nanometers. And you can calculate this wavelength using the laws of quantum mechanics. There's another line here. This is called the L alpha line. This is called the L beta line, and so on. Alright, so now let's try another gas. So atomic levels are quantized, and this quantization is really at the heart of quantum mechanics. But that's just the beginning of the story, remember. Digital circuits are also quantized. If you look at a computer and you are familiar with Boolean logic, computers work on 0 and 1. That's also digitized, and there is a barrier between 0 and 1. 0 and 1 are two different kinds of energy levels. And if a transistor that starts off in a state 0 bleeds into the state 1, then your computer is no good because you're not able to preserve what state you've initialized your registers in. So even Boolean logic is discrete. But this is just the beginning of quantum mechanics. Just for completeness, I would like to show you another spectrum which can be more complicated, but still you can see the quantization at play here. This, by the way, has mercury vapor in it. This second glass tube is filled with mercury vapor. I think I need to restart this. Alright, so now here you would see another line spectrum, but this time mercury is a more complicated atom. It has a higher atomic number, more electrons, more protons, a higher number of electrons can make transitions. So as we electrify this gas, put an electric voltage across it, the mercury atoms, some of them get ionized, some of them get excited. And as they get excited, they would always like to lower their energy because that's a tenet of nature. Everything would like to come back to its ground state. So as they come down, they fall through a cascade of discrete levels, and in each transition, they emit light of a certain wavelength, of a certain frequency. And this is what you see here. All of these wavelengths are being emitted. These are nice line shapes. Every line is a Lorentzian. But this really shows you that quantization is at the heart of quantum mechanics. But as I mentioned, we're only starting the story. There are other extremely exciting facets which really confound us. One of them is superposition, and I can't define superposition until I've given you an example of what it means. The other is entanglement. And this is the phenomenon of entanglement which really led to this Nobel Prize. Then we have interference. A really interesting, that's what makes quantum computers so special. It's interference. And that also brings in the debate of what particles and waves and duality. And then we have uncertainty. It seems that quantum mechanics glorifies uncertainty. That's the real power of quantum mechanics. It's very counterintuitive. Finally, the enigma of measurement itself. Now, I was thinking very hard about how to define quantum mechanics, and I was able to come up with these 6 basic ideas. Most of them are interrelated. And what I would do next is I would like to explain these ideas as they're normally done, as they're normally explained through the archetypal double slit experiment. And I'm sure most of you have heard about it, but are there any questions up to this point? Now, particles and waves, really interesting. I just wanted to keep this talk really accessible so that anyone who's just done 12 years of science entering into university could understand my talk. So I'm just no maths. I only have one equation, by the way. So this is like when I started learning about quantum computing, I read a very nice paper which is called The Square Root of Naught. Now, if I call this input state, I label it as 0, and I call this output state 1. So this is inverting the input. But this is a composition of 2 beam splitters. So each beam splitter is acting like a square root of naught, which is very hard to think of in mathematical terms. Now, why does this happen? This happens because the photon, if you shine a single photon into this apparatus, which is called a Mach-Zehnder interferometer, this photon takes both of these parts at the same time. It's in a superposition state. But you don't measure it. You wait till the very end to make a measurement. If you were to measure the state here, you will intercept one of the beams, and each of these detectors will follow the classical pattern. So this is, by the way, the simplest quantum computer you can think of. And you could also insert a phase medium, some kind of medium or crystal inside one of these paths, and change the length of this medium or change its orientation and get an arrangement of intensities which varies with this phase phi, such that these probabilities add up to 1. So here interference is taking place. It's taking place because we have a superposition of paths. This path is now the degree of freedom that we're talking about. The path of a photon or the path of an electron. Alright? Now another really interesting twist to this experiment. I hope I'm not speaking Greek. I hope this is somewhat comprehensible. Now, if I were to know the path, I wouldn't see interference, because path and momentum, or path and wavy nature, they are incompatible and complementary to one another. Now, another experiment that we do in our lab, remember that some of Clauser's and Alan Aspect's original experiments from 1972 and 1992, they can now be done in our lab with much more modern equipment, simpler equipment, cheaper equipment, and they could be done by 16, 17-year-old kids as well. So this is how technology has progressed over these 30, 40 years. Another property that light has is polarization. You must be familiar with polarized glasses. Now, if I have a light beam, its electric field so if this is the direction which the beam is propagating, its electric field could be vertically polarized, could be vertically pointing, right? Or it could be horizontally pointing, or it could be at any angle. And if I were to put an object called a polarizer here, and the polarizer is just like a slit or a grid of wires that lets electric field parallel to its orientation axis to go through and blocks everything else. That's how a polarizer works. So here you have unpolarized light, which means polarization in all particular directions, and I have vertically oriented polarizer, and it only lets those components go through in which the light is vertically polarized. It's like a filter for polarization. Now, an experiment that we could do is a laser and a beam splitter. Beam splitter, you already know what a beam splitter is, and then two paths. And in each path you place a polarizer. And at the end you have another polarizer, a beam splitter, that is combining the two paths and allowing for constructive and destructive interference to take place. Now, if these polarizers are parallel to one another, you wouldn't be able to tell if you were to get light here, you wouldn't be able to tell which path the light has taken because the two polarizers are parallel. Correct? So if you have a scenario in which the two polarizers in the paths are parallel, you will get fringes. These are real experiments from our lab. However, if you make one polarizer horizontal and one polarizer vertical, and you were to find out light, the polarization of light coming out of the apparatus, if it were horizontally polarized, you would be able to tell that it has passed through the horizontal arm. And if it were vertically polarized, you would be able to tell with certainty that it has gone through the vertical arm. So you are tagging the path onto the polarization degree of freedom. So if these polarizers are crossed, which means you have the which path information, you know the path of the photon, the fringes disappear. Got it? So in fact, you can also keep one polarizer fixed and rotate the other polarizer in sequential steps, click, 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 in a graded manner. And you will see these fringes, from strong fringes, they will gradually disappear. And you can do this in a quantitative manner. We physicists like not just pretty pictures, we would like to analyze these experiments in a quantitatively reasonable manner as well. So you could do a stepwise sequential experiment. Again, it's the complementarity principle, the uncertainty principle at play with real photons inside the laboratory, just around you. This is not something from Alice's Wonderland. This happens in the lab every time. So quantum mechanics has to be verified. You cannot think of any other explanations, at least I cannot think of any other explanations beyond the quantum paradigm that can describe these experiments. But the beauty is, the real beauty is delayed choice. If I were to put a polarizer at the very end, after the second beam splitter, now all the photons have made up their minds, they have passed through the apparatus. Suppose I kept the two polarizers in crossed configuration so that no fringes should be observable. I have which path information, no fringes observable, but then I am being sneaky and I put a polarizer after the second beam splitter just before the screen. I can wash away the which path information and recover the fringes. Now this is really, really astounding. The photons have passed through the experiment. You have tagged their paths because the polarizers are crossed. You have tagged their paths. You have obtained which path information, but then you are washing away this which path information even after the photons have left the apparatus. So all interference that can happen before the second beam splitter. What is after the beam splitter is not an interferometer. The interferometer is before the beam splitter, but you have destroyed the interferometer by tagging the path through the polarizers. But then, by putting an element after the interferometer, you are recovering interference. This is called delayed choice. It's like doing something in the future that is changing the course of an experiment in the past. Now, popular science writers would like to write this as a child killing his grandfather before his father was born. So this is something that is happening in the future that is determining what has happened in the past. This is only possible because of quantum mechanics, delayed choice. And it's very verifiable, it's doable, you do this all the time in the lab. This is what we done in our lab, for example. In our laboratory, we have a slightly modified version. We work with photons. This is our interferometer. Roughly the same kind of idea as you've seen in the previous examples. Two beam displacing prisms and other polarization elements. These are the fringes that I was mentioning. Here they are. Quantum interference, quantum erasure, all can be seen inside the laboratory. This is what the laboratory, by the way, looks like. Okay. Now the point is, this is so good. No one has seen an electron. Some people have. Those who work with electron microscopes, they have seen electrons. Those who work with transmission microscopes, they've seen electrons. Now you might argue, okay, I've never seen an electron. I've never seen a proton. The idea is to look at these effects in bigger and bigger objects. Biological systems, big objects. How does photosynthesis take place? Now, photosynthesis requires light harvesting energy complexes. These are big molecules, big biomolecules. How does a bird in Siberia know that every winter it has to take a circuitous path on the planet Earth and reach a lake in the province of Sindh? It's because of quantum mechanics. Now the molecule, the protein that controls this, rhodospin, is a big molecule, probably 3 or 4 nanometers across. Now the goal is to look at interference in these bigger molecules. Now why is quantum mechanics generally confined to smaller things and old things? The reason is, this is the only equation that I have, lambda equals h over mv. If the mass goes up of an object, this wavelength goes really small, really small, smaller than probably the size of the object. And when it gets really small, if you would like to probe the wavelength, the wave nature, you would like to have an apparatus that is of the same scale as the wavelength. And making these instruments and devices is really small. You can't really go less than nanometers, perhaps, in your synthetic techniques, lithography, etc. That's why it's really difficult to look at interference in macroscopic big objects. But crazy people out there would like to make world records, and they always experiment with. So this is a tetraporphyrin molecule, a tetraphenyl porphyrin molecule. This is a fluorinated fullerene, like a football, 60 carbon atoms with fluorine atoms tethered to the different carbon atoms. So they've demonstrated interference with these large objects as well. And here are the interference fringes back in 2003. Quantum biology is a new field that is coming up. I would like to work in this field, but it's a fascinating field. How does quantum mechanics explain biomolecular phenomena? Now let's come to the heart of it, entanglement. Any questions up till this point? I'll also reserve some time at the end. So I talked about superposition, I talked a little bit about the measurement paradox, talked a little bit about uncertainty, right? Interference. Now let's come, I talked about quantization. Let's come to the heart of the matter, which is entanglement. Entanglement का मतलब क्या है वैसे इंग्लिश में? Mixing up, उलझाओ, ठीक है ना? चीजों का गलत मलत हो जाना, चीजों का आपस में inextricably intertwined हो जाना कि आप चीजों को अलहदा ना कर सकें.
Like entangled hair.
जी?
Like entangled hair, like.
Entangled hair. My life is entangled in a mire of different problems which are hard to. तो ये मतलब entanglement का. A quantum entanglement is, if one were to define what's really quantumness of quantum, some people argue that it's entanglement. Now, entanglement is a correlation between, if two objects are entangled, they are correlated between them in a manner which is classically inexplicable. You cannot explain it classically. And if two objects, and if you look at one object on its own, so suppose two objects are entangled. If you look at one object on its own, if you measure its properties, you get some random output. And if you measure another object's properties in a random fashion, you will also get some sequence of outputs. And when you compare, they will be exactly correlated or anti-correlated. Now let me explain this a bit further. Suppose I have two coins, and now they are quantum coins. They're not classical coins that we have in our pockets. These are quantum coins like electrons, photons, something of this kind. And they're entangled. And one of them I keep in my pocket, and the other I give to my friend, and he goes to a neighboring, say the moon, and they're entangled. Now I toss my coin, and I get a sequence of heads, and so I'm calling this H and V horizontal and vertical, but a sequence of orthogonal states. Horizontal and vertical because I'm stuck with this polarization degree of freedom, but vertical can also mean tails. So I get a sequence of outputs, and it's a fair coin. There's a 50% probability that I get a head and a 50% probability that I get a tail or a vertical. And I assign labels to this, so I get a sequence of labels 0, 0, 1, 1, 1, 1. Now these two coins, entangled coins, are far apart. If if the other party that is on the moon were to make a measurement, he would also get a heads and will exactly reproduce the same sequence. In fact, let's call this the bearer of this coin. Let's give her the name Alice, and let's give the bearer of this coin the name Bob. These are conventional labels that they use for people who are playing this game of quantum mechanics, Alice and Bob. So Alice has one particle of the entangled pair and Bob keeps the other. If Alice gets a head, she would be sure that if Bob were to measure his outcome and differentiate between heads and tails, Bob would also get a head. Even though when Alice repeats her experiment on identical coins a number of times, her output seems to be totally random. So she's getting a totally random output, Bob is getting a totally random output, but when they convene on planet Earth again, after Bob's spaceship has returned from the moon, and they compare the sequence of zeros and ones, they are perfectly identical. And there's no chance of communication between Alice and Bob. So this is entanglement. Even though each constituent is totally random, when you look at the composite system, it's not random. So if I were to do this experiment in our lab, I have a laser, and I somehow am able to generate these entangled photons through a pair of crystals, which I've labeled here as BBO, beta barium borate. I have these two crystals. When light falls onto this pair of crystals, it produces two beams of photons. Those photons are entangled in their polarization. I get entangled photons. If I were to measure the properties of this photon and discern between horizontal and vertical, and I'm able to measure the properties of this photon and discern or distinguish between horizontal and vertical, and then if I were to compare the results, they would be perfectly correlated or anti-correlated. Anti-correlated means the exact opposite, which is also a kind of correlation. So this is entanglement at work. But the beauty and the most confounding thing is that if I were to place in each path something that rotates these photons' polarization in an identical fashion, and then I were to measure in the horizontal vertical basis, as it is called, I will still get the same result. But if I were just to measure, I would just block this channel, block B. I don't care about B. It's a don't care condition. And just look at A on its own. It's totally random. So the parts are random, but the sum of the parts is not the sum of the parts. It's just like watching a movie. So when you watch a movie and you watch it over and over again, the first 5 minutes, you watch it again, the minutes 6 to 10 are independent of minutes 1 to 5. Minutes 11 to 15 are independent of the first 10 minutes. But if this movie is internally entangled, what you observe in the first 5 minutes is going to determine what's going to happen in minutes 6 to 10. And entanglement is a correlation between the components of the composite system which cannot be explained classically. Alright, so I could measure in the horizontal vertical basis or the diagonal anti-diagonal basis. Now what was Clauser, Aspect and Zeilinger's work? Now Clauser basically created these entangled photons. He put calcium atoms in an oven, and when the atom was heated and the atoms de-excited, they emitted 2 photons. Each atom emitted 2 photons. And those photons were mutually entangled, and they went to different measurement apparatuses. And there was a perfect correlation or anti-correlation between these measurement outcomes. Now, some of the original inventors of quantum mechanics thought that this is not possible naturally. And they thought that there is something else that we don't know about these particles. There's something hidden inside these particles that is still defying our comprehension. And they call these other things hidden variables. They thought that there are hidden variables somewhere which we are not yet able to grasp, and these hidden variables are describing these correlations. So this is the idea of hidden variables. In fact, Einstein was a great believer of hidden variables. He believed that what you observe in nature is incomplete. There has to be some other theory, which means quantum mechanics is incomplete. There has to be some paradigm of hidden variables that we're not yet able to grasp. Because this is somehow defying reality. So what this experiment means is that no object has a defined property. There's no such thing as a property of an object. You change your perspective, which means you change the way you measure the object, the outcome changes. So this added some subjectivity to physics, which is, by the way, the bane of physicists. They don't want to be subjective. They claim to be elitist. They want to be objective. They don't want any subjectivity and judgments to come into their experiments. So this idea of hidden variables was stuck in our imagination. The power of Einstein, the infallibility of Einstein, made us believe that there must be something called hidden variables. But then there are other clever experiments. Alan Aspect then changed this experiment slightly. What he did is he used the same source, roughly, but then after the source had emitted the photons, he changed the measurement apparatus. Right? So an entangled pair that had been generated had no time to readapt to the changed apparatus. But even then, with the changed apparatus, there was perfect correlation. So even though the entangled pairs had been generated, with a changed apparatus, exactly the same correlation was found. And there was no time to communicate between these parties. Alright? So perfect correlation was found even though when the measurement apparatus was changed, and it was changed in a universally random fashion. There was random number generators also derived from an optical source, from a femtosecond laser that switched between these two paths. It's like a switch. Either the photon takes this path, which is denoted by a solid line, or it takes the dotted line. So changing the apparatus after the photons had been issued from the entangler, you would get the same result. So this was Alan Aspect's experiment. But then there's certain loopholes in this experiment, and the people who wanted to conform or cling to Einstein's fame and glory, they thought that still hidden variables would exist. There's still some loopholes remain. There was thought that there is some kind of some communication would be possible between these paths. So the path is determining the polarization of the photons, and some correlation might exist. But then, what Anton Zeilinger, one of the most prominent experimental physicists of our time, what he did was, for the universal random number generation, he looked at the source from two distant galaxies. So here is a cartoonic representation of two galaxies. Light is coming in from these distant galaxies, so far apart, thousands or billions of light years apart, they had no chance to communicate with one another. And the light that was coming into these observatories through telescopes determined the path that this measurement apparatus would follow. So there was no chance of communication between the two parties, because these galaxies are, thousands of light years apart, millions of light years apart. And the experiment was happening instantaneously. Ji.
So you would have entangled pairs, right? So how would you have entangled pairs in two different galaxies, and how would the physicists know?
Right. So the entangled pair is not changing. The source of the entanglement is not changing. It's some source locally available in the laboratory. These galaxies are only determining which measurement basis to use. So you have to switch between these paths, between the solid and the dotted line. This is like a random number. You toss a coin. If it's heads, you get the solid path. If it's tails, you get the dotted path. So you have to switch between these paths. So this switching is done by two distant galaxies, light coming from two different galaxies. The entangled source of electrons is not changing. By the way, Zeilinger did not use a calcium atom, he used an optical source. Got it? Now, the work of, why was the Nobel Prize given? The Nobel Prize was given for those experiments, but the work of John Bell, even though he's not acknowledged in this by the awards, is that he put this idea of hidden variables into a quantifiable test, which is called the Bell's inequality test. He came up with, so in one of the versions, which is called the CHSH inequality, the C stands, by the way, for John Clauser. He came up with this number S, and if S is less than 2, then hidden variables must exist. If S is greater than 2, if an experiment shows S greater than 2, then hidden variables cannot exist. Local realism has to be discarded. Physics, quantum mechanics is non-local, is non-real, as they call it. So what is S? S is an algebraic sum of 4 expectation values. Expectation values, each expectation value is a convex sum or an algebraic sum of probabilities. PHH, for example, is a probability. What is this? So if I look at this experiment here, 2 photons coming out, entangled photons, you have a polarizing beam splitter that separates out the horizontal and vertical photons, and you have 2 beams. And you do the same separation in the 2 beams. So PHH is the probability that a horizontal photon is found on the first beam and a horizontal photon is found on the second beam. And likewise. So you compute the sum of these probabilities, you do this experiment and find out what the value of S is. When we do our experiment, our S is larger than 2. And the uncertainty is 0.005. So you can find out it's larger than 2 by more than 150 standard deviations, which is good enough for a violation of local realism. There are other tests as well, simpler tests such as the Hardy's inequality. If H, another quantifiable metric similar to S, this is negative, local realism has to be violated. So the real advance of John Bell was that he was able to take these predictions out of the realm of philosophical rambling and philosophical sophistries into testable, quantifiable, Karl Popperian, verifiable metrics that could be measured inside the laboratory. And that's what many of the finest experimental physicists did. Okay, we can do it in our lab. Let me just finish now. We're just coming to the end. But then this has launched a wave of technologies: quantum teleportation, sending quantum states from one point to another; quantum repeaters, if you want to do long distance quantum communication, or you would like to build a quantum internet, or you would like to build a large quantum network on the global scale, this quantum information has to be preserved. The bad thing about quantum information is that it's extremely fragile because it's small and it interacts with the environment rapidly and it decoheres. The superposition just collapses. It gets entangled in other words, with the environment itself, which is undesirable. You don't want your quantum states to get entangled with the environment because that's removing the pristine nature of the quantum superposition that exists in the state. And you don't want to make it hot, because if it's hot, its energy goes up, its internal energy goes up, it's going to emit photons, it's going to emit radiation, and that's going to change the quantum state. That's why you really have to preserve this pristine quantum information, and that's why these quantum networks, quantum computers are difficult to build. You have to mitigate against what is called decoherence. That's why if you want to do long distance communication, at intervening nodes you need to have objects or machines called quantum repeaters that are also quantum mechanical that can amplify your signal. Then just two or three days ago, a really nice paper came out in Physical Review Letters, which is the flagship magazine of the physics community, in which not just two photons, but many photons can be entangled with one another. If you want to do something useful, you can't do it with two photons or two electrons. You really have to scale up your qubits, as they are called, your devices or your working qubits. They have to go up, because only then you'll be able to do something that is useful and that can surpass your classical computers or classical information processors. So you need multi-photon interference. And when you have multi-photon interference or entanglement, that's even more difficult to preserve. Okay? But then you want to build quantum computers out of it, information processors out of it. This is slightly more technical, so I'm just going to leave it. But I just want to finish off with these 2 or 3 slides. Quantum computers, I haven't talked much about quantum computers, but they come in different flavors, different variants, different technologies. You can have an NMR based quantum computer, liquid state NMR, in which the spins on the protons, they act like your qubits. Okay, and you put them inside a magnetic field. You can also have ion traps, in which you apply electromagnetic fields and you put single atoms in a row or in a circle, and you shine laser light, address these ions with laser beams, you excite them, they come down, they interact with one another. You can also have optical lattices, a Bose-Einstein condensate of atoms. You can have a photon trapped inside a cavity. You can have quantum dots, a single artificial atom that can act as a quantum computer. And the most popular are these 2 candidates these days, the superconducting quantum interference devices, SQUIDs, which are a field in their own, which have won several Nobel Prizes, these elements, in which either the current through a loop of metal that is intercepted by a superconductor, the direction of that current acts as your degree of freedom, and then you excite those currents with microwaves and so on. You can also have nitrogen vacancy centers, quantum dots. You can also have all photonic implementations, and that's where I would like to stop. These are some pictures from our quantum optics lab. Here you can see Bilal, Umair, Sabita. I forget your name, sorry. Hafsa. So this is what a simple optical 2-qubit quantum computer may look like, or quantum information processor may look like. These are some of the experimental arrangements. We can generate single photons, we can generate entangled pairs, we can do interference experiments, erasure experiments, quantum state tomography experiments in our lab. Some of our students, undergraduate and graduate students, also take this stream of in our advanced lab course. We're trying to build now large-scale quantum networks out of the work that we've done and try to help in advancing technology. So with this, I would like to end. I would be happy to take any questions. Ji.
इसमें ये हो रहा था कि जो भी वो ऑब्जर्व कर रहे थे इट्स कंप्लीटली रैंडम फॉर देम लोकली बट देयर इज अ कनेक्शन बिटवीन देम एंड देयर वाजंट टाइम डिपेंडेंट डज दैट मीन लाइक हाउ डू वी एक्सप्लेन दैट क्लासिकली राइट इंफॉर्मेशन ट्रांसफर हो रही है कि नहीं हो रही है और अगर हो रही है तो वो इंस्टेंटेनियस है और अगर वो इंस्टेंटेनियस है तो हाउ दैट नॉट वायलेट लाइक द रिलेटिविटी ऑफ लाइक मतलब नो नथिंग कैन गो फास्टर देन लाइट इफ इट्स इंस्टेंटेनियस इंफॉर्मेशन ट्रांसफर तो दैट टेक्निकली इज गोइंग फास्टर देन
Right, so you can never violate special relativity. You cannot transmit information faster than the speed of light. If you were to do a teleportation experiment, a quantum state is transported from one point to another, but there has to be classical transmission between the Alice and Bob. There has to be a classical signal that goes from Alice to Bob. So here, there you're not defying relativity. You can never have superluminal communication. But the point is that if you have an entangled pair and the two parties are separated out and there is no way they can communicate because they're too far apart. So they do an experiment at the same point in time and they compare and share the results, they're going to be perfectly correlated. There is no information transfer that is faster than the speed of light. In order to verify and validate that their results are perfectly correlated, they somehow have to share it.
Okay.
Right?
So the classical information transfer will be over.
Right. So you'll never be able to defy special relativity. That's a hard limit. Superluminal communication is not possible. And in fact, that was in Einstein's mind. Einstein thought that superluminal communication is not possible. Maxwell, when you have a charge, and a charge produces a field around it, an electric field around it, how long does it take? It cannot be faster than the speed of light. So when charges move, the field readjusts, but that readjustment cannot be faster than the speed of light. There is no such thing as action at a distance. And that's what kept Einstein from believing that quantum mechanics is incomplete, because apparently it is violating the need for the speed of light to be a hard stop. Please.